For years, archaeomagnetic dating, or Archaeomag for short, has been used in an attempt to date burned soil, hearths, kilns, and other burned features in archaeological contexts. These dates were regarded as near gospel, until now. We're Jay Kolodner, Mike Carolla, and Christina Carolis, and this is the Arcbusters. I know what you're thinking. What is Archaeomag and how does it work? Archaeomagnetism is a form of dating dependent on two important physical phenomena. The first of these phenomena is that the Earth generates a magnetic field that changes in both intensity and direction over time. The primary way this is observed is through the migration of the magnetic North Pole. The second phenomenon is that when certain materials are heated to high enough temperatures and cool back down, they take a snapshot of the Earth's magnetic field at the time of cooling. If you compare the magnetic snapshot in a specimen to a record of the Earth's magnetic field, then you can find out how long ago the specimen was heated and cooled. Archaeomagnetic samples need to be taken very carefully in order to preserve their orientation. Otherwise, the directional data wouldn't be meaningful. Traditionally, samples have been taken by carving out a column of soil, preserving this column in plaster with a cube-shaped mold, and then marking the direction of the cube in order to preserve its orientation. Each specimen is put in a spinner magnetometer that spins the specimen to measure the direction of the magnetic field. Then the specimens are subjected to a series of progressively stronger demagnetizations in an alternating field demagnetizer. This process removes the extraneous magnetization naturally acquired over time. After each demagnetization step, the specimen's magnetic field is measured. We normally put the specimens through 16 steps, and each step can take up to a half hour to do. It took over 40 hours to measure the data for this experiment. Once the cubes are demagnetized, their magnetic signal can be used to show the approximate date that the feature in question was burned.
The only problem with this is that plaster has its own magnetic charge. Hence, theoretically, the use of plaster as a medium might interfere with accurate measurement of the magnetism of archaeological specimens. This issue has in fact been raised in the literature, but given little attention. Researchers collecting archaeomagnetic dating samples in the field have always used plaster because this method and medium has been dominant for unclear reasons since the inception of the field. The issue of Plasters magnetism was noted by pioneering archaeomagnetism researcher Dan Wolfman, who was known for being especially particular about the plaster he used. He would go so far as to test every batch for its magnetic strength and use giant magnets to separate out naturally occurring magnetic bits from the plaster. However, he found that even the best plaster is still as magnetic as many of the materials that archaeomagnetists have to measure, about 20 milliamps per meter, yet he continued using it anyway. In this project, we wanted to show that even though the magnetic signals in plaster are sufficiently weak to have little effect on the dating of some varieties of archaeological specimens with an already very strong magnetic signal, many other kinds of archaeological specimens can have signals so weak that we may be measuring more plaster than specimen, and this is likely severely confounding results in some cases. We hypothesized that the use of synthetic resin, in our case an epoxy resin, or in other words a liquid plastic with setting properties, as an encasing medium, may be a better method of preserving an accurate magnetic moment of samples. Epoxy resins are thermosetting polymers with unique mechanical and resistance properties. They begin as viscous liquids but convert into rigid polymers as a result of a chemical reaction called curing. Synthetic resins are particularly attractive for our purposes because of their properties as castable, non-magnetic substances generated under controlled laboratory conditions. Such controlled synthetic conditions are in stark contrast to conditions that produce the industrial plaster that's typically used. Industrial plasters are most often composed of processed limestone or gypsum that includes its own natural biogenic magnetite signature, in addition to potentially containing a mix of other mineral inclusions with magnetic properties. In general, the control and removal of naturally occurring magnetic contaminants in plaster presents a difficult, if not impossible, set of physical issues to correct for. In this study, we tested the hypothesis that the use of a synthetic resin will produce less error in measurement than plaster due to resin's inherent lack of an endogenous magnetic signal. In order to illustrate the differences, we decided to enclose brick samples and clay samples in both resin and plaster to observe how the medium in which they were encased influenced their magnetic signatures. The variety of epoxy resin that we used in this case was the Smooth Cast 300 series of liquid plastics. These are ultra-low viscosity casting resins that boast a simple 1-to-1 mixed ratio by volume, a 10-minute cure time, and a bubble-resistant formula. We first tested controls of plain plaster and resin cubes, as well as plain brick and clay cubes in order to establish a baseline for each. We tested 3 cubes in each of the 4 categories. We then tested 3 samples of brick and clay encased in each of the media to compare them to the control readings.
Our results were quite decisive and adhered to our hypothesis. Looking at the strength of the magnetic fields of the materials, we can see already that the plaster is many times stronger than the resin. In fact, the plaster is as strong as our clay, and the resin is as weak as air. In other words, as far as the spinner magnetometer is concerned, the clay and plaster look the same, and it's as if the resin isn't even there. The strength of the brick's magnetic signal is so great that we had to make a second chart, because all of the other materials are so weak by comparison that you can't even tell them apart way at the bottom of the graph. When the brick and clay specimens were encased in plaster and resin, we also got the results we were expecting. Due to the strong magnetic signal of the brick, a signal about 50 times stronger than the signal of the plaster, and about 1,000 times stronger than the signal of the resin, there was no substantial difference between the magnetic signals of the brick on its own, the brick encased in plaster, and the brick encased in resin. In fact, the brick encased in plaster and resin both seem to be a bit more consistent than the brick on its own. This decrease in error is likely because a person can't put the brick in the spinner the exact same way every time, where the brick encased in something was so big it could only fit one way. On the other hand, the clay was much weaker than the brick, so the plaster affected it much more. Due to the closeness and magnetic intensity between the plaster specimens and the clay specimens, we were able to observe that the plaster had a significant effect on the recorded intensity and direction of the specimens of clay encased in plaster. The specimens in the plaster showed an error range of about 25 times worse than the clay on its own, and 5 times worse than the clay in resin. Additionally, further analysis showed an error was made when making the clay and resin cubes, which would entirely explain the greater error of resin cubes versus the clay-only cubes. If this experiment were repeated, their error ranges would almost certainly be the same. In conclusion, using plaster as a medium to encase samples is a rather dangerous bet. If you know your specimens will have a very strong signal, then maybe it doesn't matter. But most materials that need to be encased in plaster are actually very weak, like the clay we used in our experiment. We showed that synthetic resin, on the other hand, is almost entirely invisible and can be used even on the weakest of specimens.